Okay, next up are two more topics, one in this video, one in the next video, that deal with calculating delta H for reactions. So again, just alternate approaches to kind of be able to get a thermochemical reaction so we can build a mole to energy bridge and then go from there. This particular video is going to deal with Hess's law. Now, both this video and the next video deal with the fact that enthalpy is a state function. Now, this is kind of a hard concept to grasp, so you kind of just got to take my word for a lot of what I say, but do your best to understand the importance of the idea of a state function, all right? State functions are functions where no matter what the path taken, you get the same change. Now, remember what we care about, okay? We care about delta H. We care about the change in enthalpy of a reaction, because then that's the heat that flows during an isobaric process, and we've gone over before why that's important, okay? So whenever you see a delta, okay, what that tells you is you care about a change, and if it's a delta of a state function, right, it doesn't matter where you start and where you end up with, right? Sorry, let me take that back. What matters is where you start and where you end up. How you connect those two states do not matter. How you make the change doesn't matter. It's just where you start and where you end up with that matters. Okay? So really, when we deal with enthalpy, because it's a state function, you need to only consider reaching the correct endpoint. If you have a certain starting point, as long as you get to this point right here, between point 1 and 2, whatever these changes entail, whatever that means, just sort of as a theoretical concept, all right? Whatever you can do to get from here to here, this will have a delta H, and this will have the exact same delta H because the endpoints are the same. So that leads us to Hess's law, where what we do is we look for one total change for a target reaction. And we take, all right, this target reaction, which we'll call the overall reaction or the target reaction, and what we do is we look to add smaller reactions together to create an overall reaction. And when we do that, we can take all of the small delta H's for each of the individual reactions, okay, and add them together. Again, this will be fuzzy until we do an example problem. As we try to manipulate these small reactions to make sure we get the same change, right, we might flip a reaction. And when you flip inside a delta, any delta, you'll change the sign of that delta H. We might multiply or divide by a value. We might look at the coefficients of a reaction and say, hold on a second, these aren't useful. I'd like to change them. Whatever you do to the coefficients inside there to maintain the same mole to energy ratio, to maintain the same mole to energy bridge, you do the exact thing to delta H. Okay? Now, even though it's sort of hard to grasp that this all manifests because we have delta H as a state function, it's incredibly important. And we do this to delta H this semester, and then next semester we do it to delta G and delta S. So it's one of these scenarios where if you learn about this semester, and we only care about enthalpy this semester, but if you get this down this semester, then it makes next semester easier when you get into the more sort of intrinsic quantities associated with thermodynamics. So just as a little review, right? What we're going to see is we're going to see a series of small reactions we can put together to get an overall reaction, but we might have to manipulate these reactions. We might have to flip a reaction to make sure things are in the correct side, and we might have to multiply or divide by a certain coefficient, and we have to keep track of what we do to the individual delta H's, and then at the end, we add all the small ones together, and that makes sure that we have the correct endpoints, and then what we get is the correct value for your overall reactions delta H. Okay. This is a good video to rewatch once we go through the example, just to make sure, we'll do two examples actually, just to make sure you get the ideas down. And like I said, they kind of become clear as you look at an example, but hearing all this again will help solidify in your mind things that have to occur to do these problems correctly. So here's how Hess's law sort of problem is set up. You see a list of reactions. So for example, I'm going to give you just a general reaction A plus 2B gives 2C. So these are stand-ins for molecules or atoms. They're just stand-ins for anything, okay? They're placeholders now for us to do this example. And let's say that we have this endothermic reaction, and we say, okay, associated with this reaction is a delta H that's 5 kilojoules. Okay. I'm going to give you a second reaction, right? We have another thing, D, that can change into C as well. So the first reaction is A plus 2B gives 2C. The second reaction is D gives C. And let's say that this delta H is 2 kilojoules. So every Hess's law problem has the same structure. You'll be given 2 or more than 2 reactions at the top. These are our individual reactions, okay? Then you have a target you're trying to hit, okay? So I'm going to write the target underneath this. And the target is A plus 2B is 2D. And what you'll be asked to is, using this information and the properties we talked about before I erase, the properties we talked about at the beginning of this video, figure out what delta H is for this reaction right here. So then here's our thought process. We're going to use those tools that we described to make sure that we get the correct stuff in the correct spot, right, to hit our target. So the first step for this example problem is easy, okay? If I look at this, there's an A on this side, on the reactant side, and there's a 2B on this side. That's the only place I see A and 2B up here. So when I start this problem, I'm going to say, okay, well, I need to not do anything to this reaction because it has the correct species in the correct spots with the correct coefficients, except there's a 2C here. Now, I didn't do anything to this, right? We just justified it as a good starting point, so I'm going to write delta H is 5 kilojoules. If I don't change anything here, I don't change anything with the delta H. So I've used this. Now I go and I think about this right here. And what I see with this individual reaction is that D is on the wrong side. My target says I have to put D on the product side. Moreover, my target says, oh, your target isn't just D, your target is 2D. So what am I going to do with this reaction? I'm going to flip it, right? And I'm going to write it as C goes to D. Then, all right, I'm going to multiply by 2. Now we changed this reaction so it's delta H changed. So keep track of what we did. We flipped it. So if we flip it, we multiply by a negative sign. And then we multiplied these coefficients by 2. So then we multiply this delta H by 2 as well. So if we wouldn't manipulate this at all, right, what would be left with is a delta H that's 2 kilojoules. But we flip it, it becomes minus 2 kilojoules. And we multiply by 2, and we have minus 2 times 2 kilojoules now for that delta H. The delta H for this reaction is thus minus 4 kilojoules. So now we've used our individual reactions. And now we get this target by utilizing Hess's law, which says, okay, if I add these reactions together to get an overall reaction, which looks like A plus 2B plus 2C yields 2C plus 2D, right? Then I do the same thing with my delta H's, and 5 kilojoules minus 4 kilojoules if I add down gives me 1 kilojoules for my delta H. So you might be saying to yourself, hold on a second, we haven't hit our target, except we realize from previous chapters that when we have reactants and products, right, that are on opposite sides and no changes occurred, what do we do to them? We cancel them out, right? So these 2 C's cancel out, and then look what we have left. A plus 2B yields 2D. And what do I do to get the delta H for this reaction right here? I add up the individual delta H's, okay? So now this is just with placeholders A, B, and C. Hopefully you kind of get the general idea, but just to solidify that thought completely, or the thoughts associated with the Hess's law problem completely, please look at slide, hold on a second, I think 8. Yeah, please look at slide 8 in your chapter 5 PowerPoint. And what you'll see is a more chemically relevant problem where it's not just like A, B, and C, all right? It's actual reactants and products, okay? So what you see there is NH3 yields 1/2 N2 plus 3/2 H2, and the delta H that's given is, I believe, 69 kilojoules, okay? And then what you have is H2 plus 1/2 O2 on the reactant side gives H2O, and the delta H that's listed here looks like minus 484 kilojoules. And then just like the setup with the last problem, there's a target, right? And the target looks a little bit more complicated. It says 2N2 plus 6H2O yields 3O2 plus 4NH3. And any Hess's law problem is like this. Here's some individual reactions with known delta H's. What's the delta H for this reaction that has the same parts in it? Okay. Another opportunity to pause the video and based off the last example, even though this is a little bit more complicated, utilize the same ideas. So based off the last video, try to maybe pause this and see how far you get. Okay. So if you tried this, okay, there's a couple things to kind of realize, right? We have to do a lot more work relative to the last video to hit this target, right? Take a look at NH3. Now, NH3, right, only shows up in one place up here, okay? So I know I have to use this first reaction to make sure that this NH3 in my target is in the correct spot. So what am I going to have to do? Well, NH3 is a reactant here, and here's a product. So I'm going to have to take this reaction and flip it. But it's also, right, got a coefficient in front of it in my target reaction. So I'm going to take this reaction, flip it, and multiply by 4. Okay? So if I multiply by 4 here, I multiply by 4 everywhere to make sure that I don't lose balancing. So I flip this reaction, I'm going to get 2N2 plus, right, 4 divided by 6H2 yields 4NH3. And now we have to keep track of what we did with the delta H. The original delta H was 69, but what we did is we flipped it and we multiplied by 4. And so we have to do the same thing to the delta H, okay? And when I do this math, I get minus 276 kilojoules with 2 significant figures. So now if we look at our target, all right, we're getting closer. We got the NH3 in the right spot, and we have the N2 in the right spot, okay? But my target also has H2O. We'll look up through here. We use this guy. We only have one reaction left. We have this reaction right here. H2O is on the wrong side relative to our target. So what are we going to do to this reaction? We have to flip it. H2O has a 6 in front of it. So we have to flip it and multiply by 6. So we're going to get 6 H2O gives me 6 H2. Let me write this over here. Gives me 6 H2, right, plus 3 O2. Now, if you think about what you did to this reaction's delta H, you flipped it and you multiplied by 6. And the original delta H was minus 484 kilojoules. So we keep track of what we did, and we make sure we count for it mathematically correctly and soundly, okay? When I take minus 6 times minus 484, the number that I get out for this now manipulated reaction, right, is I get out 2904 kilojoules with 3 significant figures, right? And it's positive because the negative and the negative have canceled each other. Now what I can do is I can add these reactions together. And then I can get an overall delta H by adding the individual delta H's together, right? So let's just make sure we did this correctly in terms of our organization steps. See how there's 6 H2s here and 6 H2s here? These will cancel. I'm going to get 2N2 plus 6 H2O, yielding 4 NH3 and 3 O2. Does that look exactly like my target? And the answer is absolutely yes. So if I can add these individual reactions together, then my total delta H for my target reaction or my overall reaction is found by adding these. Paying attention to significant figures then, if I take 2904 and subtract 2976 through that addition step, what I get is 2628 kilojoules. But this number is good to the tens place and this number is good to the tens place, so my answer is only good to the tens place. And so my final answer then is 2630 kilojoules. We see that it's an overall endothermic process. Okay, so it's worth seeing 2 examples, but this is it for Hess's law. It's this same logic structure every single time. What do I have in my individual reactions? How do I get them in the correct spot? With the tools of flipping or multiplying and dividing by coefficients. And then whenever you have to flip or multiply by, or divide by coefficients, you do the same thing to the individual delta H's, and at the very end, you just add down, okay? And if you bookkeep everything correctly, it becomes just a sort of simple process that you enact again and again in the, in the different examples that you'll see in your book and in your Chem 101 homework, all right? One last chapter 5 topic to talk about next time, and that deals with using standard enthalpies of formation.